last time when we talked about VSEPR theory
Yeah.
and electron shapes and molecule shapes, the biggest takeaway from that introductory video was this tetrahedral shape, remember, with each of these being a lone pair. And so I believe all of our examples from the beginning video, the electron shape was tetrahedral, meaning that there were 4 lone pairs or 4 bonds of sorts in the molecule. Today, I'd like to discuss what happens when we have different electron shapes in our VSEPR theory.
Okay.
And so this shape is when you have 4 different electron groupings.
I think that would be an okay way of describing it. At one point, we will talk about them as being tetrahedral and using molecular structures like this. And then at some point, we will discuss them as being sp3 hybridized, right? So depending on where in the course you're watching this video, you might see this as being 4 electron pairs, each pointing away from each other as far as they can at 109.5 degrees. Or we might be describing them in terms of, hey, each one of these bonds has some S characteristic and some P characteristic. And so we might say they're sp3 hybridized, and tetrahedral is sp3 hybridized.
Yeah, exactly. So this would be 4 different groups, or sp3 hybridized, as Dr. Hunter mentioned. But if we now look at this molecule, this is methane, or C2H4, and
Right.
I'll kind of move it around a bit. As you can see, we have this new kind of bond. It's unlike the straight bond we see right here between this carbon and hydrogen. Between the 2 carbons, there seems to be 2 lone pairs, or so that would be 4 electrons between these 2 atoms, correct?
Correct. Yes. Yeah. I mean, the first most important thing I think to notice there is that each of those carbons still has 8 electrons.
Exactly. They still all follow the octet rule, or with the hydrogens, the duet rule. And so this is still a viable molecule.
Right. But the angle with which those bonds are arranged around each one of those carbons is not tetrahedral, and it is not 109 degrees. They're actually, if you tilt it a little bit more towards the camera, we'll see that whole molecule is actually flat.
Correct. If I just lay it on the ground like this, you can see
it's pretty. It looks really pretty flat there. And so those 3 around each one of the carbons that has 2 hydrogens and 1 other carbon, there are 3 atoms bonded to each carbon, and so that's flat. So they are 120 degrees, but it is no longer sp3 hybridized. It's a different organization of bonds that make those double bonds and make that molecule flat.
Yes, exactly. So because, as Dr. Hunter mentioned, it's not 109 degrees, it looks more like 120 degrees. This electron shape around the carbon would be considered trigonal or trigonal planar, because, as we've been talking about, the molecule is pretty much flat, and that 120 degrees, looking at the electron shapes, So only these bonds makes it trigonal planar. And at the same time as well, we can see that the atoms around the carbon are also in that same shape. So the electron shape is trigonal planar, and so is the molecular shape around the carbon.
Right, right. Okay, and the one other consequence, which students who watch this video who will also read in the textbook and use the online Cengage chapter, they'll see that this bonding has s orbitals going between the two carbon atoms, and two of the p orbitals on the carbon atoms overlap. And so this type of bonding we call sp2 hybridized.
Yes, exactly. sp2 hybridized. I also have some more examples
Okay, let's
of
see what else
other
you got.
molecules.
Let's see what else you got.
And so this is when we have an sp2 hybridized atom,
Yeah.
or three different directions, you could say, that all of the electrons are going in instead of the four. If I bring out carbon dioxide, CO2, we can see right here, this carbon right here still has 8 electrons around it. It has 4 bonds, 1, 2, 3, and 4, but it only has 2 atoms around it, and the electrons are going in only 2 directions, right?
Correct. It's definitely linear.
Yes, exactly. And as Dr. Hunter already said, the electron shape is linear and the molecular shape is linear because of the only 2 groups, whether we're talking about the electrons and the bonds or the atoms around the center atom.
Right. And I think this is sp2 hybridized as well.
Yes,
Do you agree with
correct.
that?
Yep.
Because each one of the bonds from the carbon to the oxygen uses some of the s orbital and the two of the p orbitals that can overlap with the oxygen's p orbitals to make it sp2 hybridized. Let's back up here for a second. The oxygen is sp2 hybridized. The carbon is sp hybridized.
Yes. That's correct. So if I were to show the other electrons that aren't around the oxygen, which I can't attach, but they are there.
Right. So we can see, so if we focus on the oxygen again, can you bring in that C2H4, sorry, C2H4. Okay, so now if we look at the red oxygen that you're identifying there and the carbon in the adjacent molecule, they both have a double bond and they both have 2 other pairs of electrons. And so both of those are sp2 hybridized. But the oxygen that's in the black oxygen that's in the center of the 2 red oxygens, it is sp hybridized because it only uses one of its p orbitals to point directly at the oxygen atom in the carbon dioxide molecule.
Yes. So to clarify, if anyone is still confused, these 2 oxygens are similar to these two carbons in that they are sp2 hybridized. I can do this and this to represent the not shown electrons,
Yeah.
but this carbon right here is only sp hybridized.
Yeah. Correct.
I prepared this triple bonded CN ion.
Okay.
And so CN, carbon and nitrogen,
Yep.
and it is triple bonded.
Yep.
You can see there are 3. And just for clarification, I'll add this lone pair that's on the carbon.
Right.
And so the carbon and the nitrogen, there's also a lone pair on the nitrogen, which I can't attach, but it would look like that. Both of these atoms would be sp hybridized, similar to the carbon in the center of this molecule, of carbon dioxide.
Right. So that's sp3 hybridized, sp2 hybridized, and sp hybridized, right? And
Yes.
if you were to, and so from in this video going from right to left, if I've got the other right, if I've got 4 bonds, it's sp3 hybridized. If I've got 3 bonds, it's sp2 hybridized. And if I've got 3 bonds, it's sp hybridized. It's interesting that one of the numbering systems goes down as the other numbering system goes up, but that's it is a context based way of trying to understand how these molecules can fit together, how they can be stable, how they can be bonded, in terms of us understanding that carbon wants to have 8 electrons in its outer orbitals. And so by sharing those 8 electrons in a hybridized way between the central carbon and whatever it's bonding to, we can justify a lot of the physical and chemical properties of these molecules.
Mm-hmm. And I'm also glad that you mentioned context as well, because for some students, you mentioned that 4 bonds, 3 bonds, and 2 bonds as we count the hybridization. But also remember that there are still 8 electrons. We just count this double bond, even though in the name it's double. We only count it as one entire bond when in the context of VSEPR theory and in molecular and electron shape. The triple bond in the name, it would mean 3 bonds. But in the context of VSEPR, it only counts as one main bond or one main grouping.
Right. So in the right-hand side, we have carbon attached to 4 atoms, sp3 hybridized. In the middle molecule, we have carbon attached to 3 other atoms, sp2 hybridized. And in the left-hand one, we have carbon attached only to 1 other atom, and it's sp hybridized.
Yep.
There's a lot going on in there.
Yeah, certainly. You just need to familiarize yourself with the VSEPR theory and electron shape, molecular shape, and all that, because it is fundamental in this course.
Yeah. Well, thank you. Thank you. I appreciate you leading us through this one.
Thank you, Dr. Hunter, for tagging along as well.
Yeah. All right. Talk to you next time.
Yep, talk to you next time.